Welcome to the Deep Dive. We're continuing our series for number theory students, exploring really fascinating corners of the OEIS. Today we're jumping into sequence A000327. It's got this intriguing name, number of partitions into non-integral powers. This sounds quite, well, abstract at first. We're lucky to have a distinguished mathematician with us to help break it down. Just to give you a feel for it, the sequence kicks off 1, 5, 12, 23, 39, 62.
It's a pleasure to be here. Yes, partitions into non-integral powers. It's a bit different, isn't it? Normally when we talk partitions, we think about summing whole numbers, like 5 is 3 plus 2 or 2 plus 2 plus 1. But here we're looking at sums that involve fractional powers. That shift changes things quite a bit.
Okay, so that sets the stage. How do we actually get those numbers? What's the precise definition behind that 1, then 5, then 12?
Right. So the sequence A000327 counts the number of solutions for a specific inequality. It's by 1 raised to the power of 23 plus by 2 raised to the power of 23, and that sum has to be less than or equal to n.
Okay, ups 1, 23 plus by 2, 23 equals n.
Exactly. And crucially, by 1 and by 2 need to be distinct positive integers. So 1 replaced by 1 by 2. You can't use the same integer twice, and they have to be positive.
The distinctness and that 23 power, that's what makes it different from, say, sums of squares.
Precisely. That non-integral exponent takes us into less familiar territory.
Now, what's really interesting to me is that this sequence isn't, something somebody just cooked up recently. It has a history, right? I think Sloan featured it.
Oh, absolutely. It has quite a pedigree. N.J.A. Sloan included it in his original A Handbook of Integer Sequences back in '73.
Wow, 1973.
Yes. And then again in the much larger Encyclopedia of Integer Sequences in 1995. The fact that it made the cut in both really speaks to its mathematical interest. Sloan clearly saw something special there.
And the story gets even richer, doesn't it? Because it doesn't just live in the world of pure math. There are connections elsewhere.
That's perhaps the most surprising part for many. There's a fascinating link going back to a 1951 paper.
Yeah, 1951. Even early.
Yes, by Agarwala and Alok. The title is quite revealing. Statistical Mechanics and Partitions into Non-Integral Powers of Integers.
Statistical mechanics, how does that connect?
Well, think about modeling physical systems. Sometimes energy levels or particle states aren't nicely described by simple integers or integer powers. This kind of partition, with non-integral powers, can potentially model aspects of complex systems, maybe certain energy distributions or configurations in statistical mechanics.
So like describing phenomena that are more continuous or less neatly packaged than standard models allow.
Exactly. It shows how these abstract counting problems can, sometimes quite unexpectedly, provide tools or frameworks for understanding the physical world. It's quite beautiful, really.
It genuinely is. Okay, so for listeners who are intrigued and maybe want to calculate a few terms themselves or understand how it's computed, is there a formula?
There is, thankfully. Seth Troisi found a rather neat formula for AN, the nth term. It's given by AN, 8N0014N02.
A00148, I should know that one. That's related to sums of two squares, isn't it?
You got it. A000148N counts the number of integer lattice points, xy, such that x squared plus y squared is less than or equal to n, essentially points inside or on a circle.
Huh. So this sequence, A000327, is derived from counting points in a circle adjusted by this floor term involving n.
That's the essence of it. It connects our non-integral power partition problem back to a more geometric counting problem. Quite an elegant link between algebra and geometry there.
Fascinating. So wrapping this up, we've looked at A000327, defined by this inequality with the 23 power. We've seen its history with Sloan, and this really surprising connection to statistical mechanics from the 50s.
Indeed. It really drives home that mathematical sequences, even ones that seem quite specialized, can have these hidden depths and connections. From how we compute them using other known sequences to how they might describe physical reality, it's a great example of math's interconnectedness.
Definitely. It leaves you thinking, what if we changed that exponent? What if it was 12 or maybe 45? How would that sequence behave? Or where else might these kinds of non-integral power partitions pop up? Perhaps in biology or economics, something to ponder. Thank you for joining us on this deep dive into AS000027.